So on this note, I'd like to introduce our second speaker, Matthias Naaf, who will talk about stratified Datalog.
Yes, thank you very much, and also thanks for the opportunity to be a part of this workshop. So I'm Matthias, I'm a PhD student in Erich's group in Aachen, and I'm close to finishing my PhD, and during my PhD, well, Erich has already told you a lot of what I have been working on, so Semiring Provenance for logics and games in general. And today I want to talk about one of my favorite results of this time, which is more of an algorithmic result. And to better fit this workshop, I want to, well, phrase this a bit in terms of stratified datalog. So the title is quite long, so let's break it down a bit. Well, we have already seen what Semiring Provenance is, and I will start by very briefly introducing how we can define such a Semiring semantics or Semiring Provenance also for stratified datalog. And mostly in this part, I want to try to convince you that we somehow need greatest fixed points when doing this. And then the algorithmic aspect is, of course, how can we compute these fixed points? And how can we do so efficiently? And this will be the main result of this talk. And then once we have this as a nice application of this, we can also define circuit representations to efficiently store this provenance for stratified datalog. So I will be a bit quick in the first part. So if you're not familiar with datalog, it might be a bit difficult to follow, but don't worry, because the main result does not depend on datalog, so you will still be able to follow this. So let's start. Why do we need greatest fixed points to define this semantics for stratified datalog? Let's first look at datalog, because this was basically where this entire framework of Semiring semantics was initiated in 2007 in this seminal paper by Green, Kavanarakis, and Tannen. And datalog is a rule-based query language like this, for example. We read the rules from right to left. So in this case, if we have an edge, then this means that this tuple xy should also be in the relation T that we are defining. In this case, it's the standard example of defining a transitive closure. So the second rule means that if we have an edge from x to z, and we can already go from z to y, then we can also go from x to y. And we evaluate such a program on a database. In this case, we can present this database as a graph like this. And to define the semantics, I want to take a slightly unusual way of defining it by means of equation systems. They look like this. So basically, for every candidate tuple that we have, like, for example, UW, we write down an equation when this tuple will be in the relation T. So either we use the first rule, then we need a direct edge D, or we use the second rule, then we have two options in this graph, either using edge D or edge A, and then relying on another tuple of the relation. And to switch to Semiring semantics now is very easy. We just replace the operations by Semiring operations, and we are done, basically. And the semantics of this is that we compute the least solution to this system, and doing so in different semirings gives different results. For example, in polynomial semirings, we get basically all ways to go from U to W. In power series, we get all of the paths to go there. In absorptive semirings, we only get the shortest ones, where we do not do any loops. For example, here, the semiring of positive Boolean formulae. We could also do a bit different things. We can use, instead of abstract tokens, we can annotate the edges by cost values, and then the same equation system gives us the minimal cost of a path from U to W. The only requirement is that all these semirings are omega continuous, which basically just makes sure that these least solutions always exist. Now let's move from this to stratified datalog. The idea is that we want to add negation to our language, but oh, there's a question already?
Slides where you define provenance by saying it's the solution of the equation system. If I'm used to the definition of provenance as considering all derivation trees, is this the same thing? Is it obvious that it's the same thing?
I'm not sure how obvious it is, but it is the same thing, yes.
Okay.
Yeah.
So you tell this solution with regard to what order?
That's a good question. We also use the natural order here of the semiring, so the one induced by addition. Okay. So for stratified datalog, we now want to include or add negation to the language. We cannot do so in any way, because if we define a relation by its own negation, this does not lead to a well-defined semantics, or at least it's not clear, or one has to be careful to define the semantics. So in stratified datalog, we arrange the program in layers or stratums, and the idea is that once the first layer is complete, we are then allowed to negate this predicate here. Because then it will no longer change, so we can now apply the negation here. Now in semiring semantics, if we deal with negation, then what we do is we annotate every edge in our graph both by a positive annotation and by a negative annotation whenever we use the absence of this edge. And well, how can we now define the semantics? Well, in some semirings it's easy. We can just directly define a negation operation. For example, in post-bool we can just, well, take the positive Boolean formula and negate it. And also for these values here, we switch to the negative annotation then. That's fairly easy. But it's not so obvious in all semirings. For example, in polynomials where we have exponents, it's not really clear what to do with these. And also for a tropical semiring, what is the negation of a cost like 7 or a cost like 0? It depends on the application what would make sense here. It's not so easy to define this in general. But we want a semantics which works for a wider class of semirings and should give the same result as this one here for post-bool. And the way, I think the easiest way to define this in general after we did some thinking about different versions is again by something like a negation normal form. So we want to push the negation in. And if we have these equation systems, there's a particularly easy way to do this. We just take the equation system for t, this one. And now to express the negation of t, we just dualize the system. So that's basically the same as negation normal form in some sense. So here we just replace the operations and switch between the positive and the negative annotations. Now the thing is, because this one here requires the least solution and we now dualize the system, now here we have to compute the greatest solution to this system in order for this to really capture this idea of the negation normal form. And the semantics defined in this way has the properties we want. It's applicable to a wide class of semirings, absorptive ones, but also non-absorptive ones, but we only look at it for absorptive ones. And it gives the same result as the direct implementation for the post-bool semiring. Okay, so that's one motivation for greatest solutions. There is another motivation, which was in fact my primary one, because I was looking not at Datalog, I was looking at fixed point logic. And there you can do something like say that there is an infinite path from a node by this formula here. We don't want to read it also because it contains a typo here. And if you evaluate this on a graph like this, 3 nodes graph, where again we use the tropical semiring to annotate these edges by cost values, then you get again an equation system similar to the ones before. For example, for B, we have 2 options, either pay 1 plus the cost from A, or pay 20 plus the cost from C. And again, it's the greatest solution here that we want to compute, because this will then give us the information what the cost of the infinite path is, the minimal cost of an infinite path. Okay, so in both of these cases, you want to find greatest solution of these equation systems, and this is what I want to talk about now. And also, I want to explain why I'm always talking about greatest fixed points, although there's always greatest solution on this slide. This is simply because if you have an equation system like this one, it's more convenient to view this as an operator defined by polynomials on the right-hand side. And then you want the greatest fixed point. Yeah, so if you missed out on any details about Datalog, now is the point to join back in, because this is now a question which is independent of Datalog or any provenance analysis. We just want to find the greatest fixed point of such an operator which has polynomials on the right-hand side. Right? This doesn't look polynomial, but it's polynomial in the tropical semiring. What's the naive approach to find this fixed point? You just start from the greatest value, which in the tropical semiring, you just have to trust me on this, is the 0 element, because the natural order by addition is somewhat flipped in the semiring. And then you repeatedly apply the operator until you converge to a fixed point. And indeed, you converge to this fixed point here. It's the same from the last slide. 2 things come to mind. First, it takes very long. So it's not feasible for computation. And secondly, you see that the pattern changes after 20 steps. Why is that? Because we have a coefficient 20 in our system. This is also a bit bad because we want the complexity to not depend on the coefficients, but only depend on the number of equations that we have. Okay, is a question? Yeah?
Are you starting from zeros of the semiring or ones of the semiring?
We are starting from the 1 element of the semiring in general, which in case of the tropical semiring, somewhat confusingly, is the 0 element. So, but I think it's easier to understand the tropical semiring, so I will stick for this talk, I will stick to the tropical semiring, because I think besides this small confusing part, most of it is easier to understand here. Okay, so can we achieve this? It turns out we can. So this is the main result. If we have an absorptive fully continuous semiring, I will explain this, but you've also seen it in the last talk. And we have this operator in n equations induced by polynomials, and the least fixed point is just iterate the operator n times. Now this is something which has been known before. And the new result is that for the greatest fixed point, we can do it similarly. We iterate n times from the 1 element, Then we have this special operation here, which I will explain. Then we iterate another round of n steps. Intuitively, if you think of an infinite path, if it's a lasso path, it has this reachability part and this looping part. And this here accounts for the loop. This does the repetition of the loop. And this is the reachability part, basically. OK. So in our example, this means it looks like this. So we first do these n iterations, then apply the special operation, and then do another round of n iterations. In this case, we don't need all of these n iterations, but in general, you need all of them in both places. So you can still compute this in a polynomial.
N is the arity of the operator. What is?
Yes, n is.
And you only need n iterations and some.
Yes, so n is the number of variables that we have, or the arity of the tuples that we are operating on.
So is n 3 in your example?
Yes. It's the number of entries here.
And you're saying it's enough to iterate it 3 times? Is that 6 times?
I mean, for the least fixed point 3 and for the greatest, 3 plus the special operation plus another round of 3, yes.
I think we are puzzled by the example. So apparently you are telling us that in this example, it suffices to iterate 3 times, do that infinity mumbo jumbo, and then iterate 3 times again, and that's it.
Yeah. In this example, it would suffice to do only 1 iteration here and then immediately do this. But in general, you need all of these iterations. Okay. So I want to talk a bit about how one can prove this so that you get an idea of the tools that we use for this. But first, I wanted to talk a bit about these conditions on the semirings. Now, we have already heard about this in the last talk, so I can keep this short. We use the natural order to answer your question from the beginning, so defined by addition. And then we require that we have a supremum and an infimum of every chain, because we need both, basically. So this is the technical condition that we need, and you can mostly forget about it. It's not very important for this talk. The important condition is absorption, and this is the one which we technically do not need. So we could also define the semantics for a Stratified Datalog without absorption. But as Erich said, it turns out that we get meaningful information if we assume this. Also, another nice thing is we get that the semantics works well with continuous homomorphisms. This is something which does not work in general semirings, but it does work in these absorptive semirings. And well, this is absorption for all elements A, B. We have this equality. It's actually equivalent to these other 2 notions. So the semiring is 1-bounded, and also that multiplication is decreasing. And this is the one I want you to remember. So I've made a picture for this where multiplication is going down, because that's the one we're going to need. And also this explains that we have some duality between addition and multiplication, which is the intuitive idea why absorption is helpful here. Okay.
Yeah, so absorption isn't necessary for the result on the last slide?
Yes, for this result it's necessary. Sorry, but to define the semantics for Datalog, for Stratified Datalog, it is not necessary.
I see. And then for least fixed point, I'm familiar with requiring plus and times to be monotone, and then here you're requiring it to be decreasing. So would that create a problem for least fixed point?
No, they are both monotone.
I see. Yes.
You can show this. Yeah. So addition is monotone because of this, I think, and multiplication is monotone
because of the distributivity.
Yeah, because of distributivity, exactly. Yeah. Okay, so now we have that multiplication is decreasing. So if we multiply the same element repeatedly, we get a decreasing chain. And this converges. The infimum of this is then some value because of our assumption here. And this defines this infinite power operation. Just repeatedly multiply the value and take the infimum of that. Okay, so these are all the ingredients we need. Now, how can we prove this result? On a very high level, it takes only 2 ingredients, derivation trees and absorption. So let's see how these work. What are these derivation trees? I think it's a common concept. Here we again have an operator. I chose a more complicated one than before because the first one was linear. The trees would be not very interesting. This one is nonlinear because we have these 2 indeterminates here. These trees are defined as you would expect, basically like for a formal grammar, for example. You start by x, and then you have 2 ways. Either use this derivation of paying 5, or you pay 1 plus the cost of x and y combined. In this case, I chose the latter option, pay 1. So this is supposed to be a price tag. And then here we have x and y and continue the tree from there. Here I stop, paying 5, and here I continue, and so on. This defines a tree, in this case an infinite one, and the cost of this tree is simply the combined cost. In this case, it's infinite. There are, of course, also finite derivation trees. Now, I'm not the first one to look at derivation trees in the context of fixed-point computation. In fact, I was inspired by this very interesting line of research on Newton's method in semirings some 10 years ago, which Javier will give a talk tomorrow, so I don't want to spoil anything here. But the idea is to take Newton's method to approximate zeros of polynomials, which uses derivatives, and generalize this to semirings to compute fixed points. And it looks something like this. I don't want to take credit for the Photoshop skills. I stole this picture from a presentation. But so in my terminology, what one can say here is that the least fixed point can be expressed as the minimal cost over all the finite derivation trees in these absorptive semirings. And what I'm now saying is that the greatest fixed point can be expressed if you also take the infinite trees into account. How to prove this correspondence between trees and fixed points? Well, we start from the fixed point iteration. And if we take the minimum over the cost of all the trees, so we cut the trees off after the first layer, we get the first iteration step. If we cut them off later, we get the subsequent iteration steps. Now the difficult part is to show that what happens if we apply the infimum. So on the right side, it converges to the greatest fixed point. That's easy. On the left side, it converges to the minimum over these entire trees. This is easy to prove for least fixed point, difficult to prove for greatest fixed points because these trees are now infinite. And so we basically have to show that the infimum commutes with this minimum, or in general with the supremum. This does not hold in arbitrary cases. It works here because these trees are defined by polynomials. So they are finally branching and well-behaved in a sense. But that's the first difficult step. Now remember what our starting point was. We had this infinite iteration, and I said, well, it's bad. It's infinite. It's difficult to compute. Now we have achieved this. We have greatly simplified our lives. We now have just to compute the cost of infinitely many infinite trees. It's much simpler than before. But it becomes simpler once we apply absorption. So this means, again, multiplication is decreasing. Or to put it simpler, in the tropical semiring, all we have to care about is we have to count these price tags, these coefficients. If they occur more often, every price tag occurs more often in one tree compared to another tree, obviously the first tree is more expensive. And that's all we need to know, because we only want to compute the minimum of these trees. We can then only look at the second tree. So the idea is, instead of looking at a very difficult tree like this one here, obviously very, very irregular and difficult, we transform it to a nicer tree, which is easy to work with, and show that this does not increase the cost. How do we do it? Well, we check which of these tags occur infinitely often. Let's say these are the ones, and we look where they first occur in the tree. Let's say these are the first occurrences. Then we cut the tree off there. And from there on, because they occur infinitely often, also some of the derivations must occur infinitely often, and so on. And we commit to this. We always do the same derivation from these indeterminates. So we get a tree which is deterministic or periodic, in a sense, which is already nicer to work with. We still have this prefix here. It could be large, but everything here appears only finitely often. And well, if we have a repetition, then clearly it would be better to just avoid the repetition and directly do this part, because then the cost will only be smaller. And then we obtain nice trees which have a prefix of at most height n, because after n we must have a repetition, then followed by these deterministic or periodic trees. They can still be infinite, but they are easy to understand because they repeat the same pattern over and over. And for the minimum, it suffices to work with these nice trees.
How could the minimum cost tree be infinite?
Sorry?
How could the minimum cost tree be infinite?
How the minimal cost could be infinite? I mean, if there is no way if there is no finite tree.
I see.
But also you have to take into account that this is a bit of a simplification here, because here minimum, so it's particularly simple in this semiring because we have the minimum operation. In a general semiring, we don't have a linear order. So we don't have a minimum, we have a sum. So then every tree contributes something. It's not just a minimum. But even here, it can happen that we have to look at these infinite trees, actually. Because the infinite tree could have finite cost, and it could also be that there is no finite tree at all.
So in the tropical semiring, this can only happen if there is no finite tree.
Or there is an infinite tree where this infinite part here has cost 0. This could also happen. If some edges are free, if you do not have to pay for them, then And you would also need these infinite trees. Yeah, otherwise you're right, I think. Okay, so now we have these nice trees, and all that is left to do is to prove how we can compute these. And this is obviously, this is a bit technical, but I don't want to go into details here. The idea is as follows. If we zoom in on this deterministic part, we have the same pattern repeated. And I said that iteration corresponds to trees. So if we do n steps of the iteration, it covers basically everything that happens in trees of height n. So it covers this pattern that is repeated. And if we just apply this infinite power operation, it accounts for repeating this tree infinitely often. We still have this prefix part. This prefix, again, remember, n layers correspond to n steps of the iteration. So we just do n steps, but we start from the value of these child trees here, which is covered by this expression. So we obtain this expression in total, and this proves the main result. So this is a bit technical, but once we have these nice trees, this is relatively easy to do. So the key ingredients really are that we have a polynomial operator and that we have absorption to simplify these trees. Now, I think I still have a few minutes left, so I briefly want to talk about how we can apply this back to Datalog to define circuit representations, because the title was algorithmic aspects. That's a plural, so there need to be another application here. And what we have already seen before or mentioned before is that this provenance information, it can become large. So we can efficiently compute these greatest fixed points. It takes only a polynomial number of operations, but if each operation doubles the size of the polynomial, we still have an exponentially large polynomial in the end. And this is not avoidable. For example, here, the transitive closure of this graph has to be exponential because there just are so many ways to go from u to w, as you can see. So we cannot avoid this in general, but what can be done and what has been done in this 2014 paper is to define circuit representations to encode this polynomial more efficiently. Now you could argue that in this case, a nice encoding would be the graph itself. And this will work as well, but of course this approach works in the general case. How does it work? Well, we already have these equation systems, so we can just use them and turn them into circuits. So we have two layers, this addition node, and then for each monomial, this multiplication node. And then we have a semiring value or an indeterminate. We can do this for every equation of the system, so we get a layer, and this layer can be stacked. How often do we have to stack this layer? This is a question that every one of you should now be able to answer. Of course, n times, because the least fixed point is reached after iterating n times. Right? Each layer is basically one iteration. We start from 0. Now, of course, we connect these layers so that the indeterminates here are connected to the corresponding roots of the next layer. Now we want to turn this, apply this approach to Stratified Datalog. And we can do this. Remember, the idea was that we dualize these equation systems, and we can just do the same on the circuits. So we take the circuit for t, and now dualize it to obtain a circuit for the negation of t. Except that here we need the greatest fixed point, which is not necessarily reached here. In some semirings it is, like in post-Boole. In other semirings it's not. So we have to adhere to this expression and add another round of n steps and this intermediary layer in between. So assuming that it's fine to use this operation, and in fact this operation is usually very easy to compute in semirings, then we also here have a circuit representation now, which is still of polynomial size. Okay, and that's, there are some questions. Yeah?
Can you explain that infinity operation?
Yeah, that's exactly what I wanted to ask. So
This infinity, this is this infinite power operation. So it's basically the infimum over, so basically you take an element, you multiply it by itself, and you get a downward chain of this, and it converges with some
finite number of steps.
No, it does not converge in a finite number of steps in general.
So then how would that guarantee the size of the circuit if we
Yeah, so that's the point. I think there is no general way to have a circuit to compute this, but in all the semirings that we are looking at, this is actually easy to compute. So if you have a polynomial, for example, the semiring of generalized absorptive polynomials that we have seen in the last talk, you just replace every exponent by infinity. If you use a tropical semiring, you just multiply by infinity. So in all of the semirings that I have looked at, it's very easy to compute this. But you have to be able to do this in order to have this circuit representation.
But is it semiring, like
can I define an operator that only is dependent only on the semiring and not on the actual data, right? So
Yeah,
the
it-
operator takes I can read as a function that takes an element of the semiring and spits out an element
Yes.
of the semiring.
Yes. But it will be different for different semirings, yes. This was both of your questions. Another question?
So let me do a sanity check. So if we have the polynomial x equals x, is it true that the least, over the tropical semiring, is it true that the least fixed point is infinity, but the greatest fixed point is 0?
You mean you have the identity operator, or?
We have a polynomial x equals x over the tropical semiring.
Mm-hmm.
Is it true that the least fixed point is infinity, but the greatest fixed point is 0?
Yes, I think so, yeah.
Okay, thanks.
Okay, so if there are no further questions, then let me conclude the talk by a brief summary. So the main result here is that we can compute greatest fixed points in absorptive semirings, also assuming this continuity assumption, which is more technical, by combining these trees and the absorption property. And then there's also some connection to stratified datalog. So we can define a semiring semantics for stratified datalog by this idea of negation normal form, which we can implement here by dualizing these equation systems and then computing the greatest solutions. And this can also be turned into circuit representations. And now, to end this talk, I have two open questions. The first one is actually slightly embarrassing because we are still looking a bit for applications of this semantics. So to explain this, our motivation is more a theoretical one. We wanted to look how far can we push the semiring framework to which kind of logics. And for these fixed point logic, we have this nice application of strategy analysis in infinite games. But these games are not expressible in stratified datalog. So here we would need something else. We can do a lot of things like how provenance and repairs of databases, but these can all be done in the post-spool semiring, which is simpler. The question is there also an application which needs, for example, the tropical semiring or more general absorptive semirings? And the second question is on alternating fixed points, also something which is not present in stratified datalog, but which is present in fixed point logic. So the first part is, if we have a greatest fixed point that is defined by a least fixed point inside, can we still apply this formula here? Because this one assumes the operator to be polynomial. But what if there's a least fixed point inside? Spoiler, the answer is yes, we can. But it's not, I think it's not immediately obvious why this is the case. And then what's the complexity of this? If we have an alternation depth of n nested operators, usually the approach is exponential in this depth. But there have been these quasi-polynomial breakthroughs for parity games, which are also applicable to alternated fixed point evaluation. And these work for the Boolean semiring and also for finite height lattices. And so I think absorptive semirings might be just on the border of where this result can be generalized to, because they can be infinite. We can have infinite iterations, as we have seen. But still, we have these relatively easy ways to compute these fixed points. And so this would be really interesting, but I don't have an answer to this yet. This really is an open problem. That's all. Thanks a lot for your attention, and I'm happy to take further questions.